All right, so let me do this and the next question together. They both involve forces being added in 2 dimensions. So I'll just do them together and I'll approach them in a standard way. And really the standard way to add forces, especially when you have to treat them as vectors, 2-dimensional, 3-dimensional vectors, is to add by components. So let me first write down the information that they are giving us. So they give us, so let me define my axis so that I have some components. I think the kind of the same thing to do here is to define my x and y axis the normal, usual way. So the question is asking for the moon's acceleration while giving us the forces. So what we need to do is we need to use Newton's second law. The net force is equal to mass times acceleration, or that acceleration is given by the net force divided by mass. So they are only asking for the magnitude, so we don't need to figure out the direction, but I still need to figure out the net force component or the acceleration component in order to calculate the magnitude. So let me do it this way. I think I'm gonna figure out the net force component, and from that I will be able to calculate basically the absolute value or the magnitude of the net force, then divide by m, which will give me the magnitude of acceleration. So let me first write down the two forces that I'll be adding. I have my FEM. I think that's the force on moon by Earth. So they gave us some number. Let me write it down with the unit vector notation so that I will remember how to add it. So it's going in the y direction according to the axis I defined. So its x component is 0 x hat, plus the y component 1.98 times 10 to the 20 Newton y hat as a vector. And the force by the sun on the moon, FSM, is only in the x direction, the way the axes are defined here. And that's 4.36 times 10 to the 20 Newton x hat plus 0 y hat. So when you are calculating the net force here, it's pretty simple, because the two forces you are adding, they only have basically one non-zero component. So when you add them, the other is 0. So the net force is gonna be 4.36 times 10 to the 20 Newton x hat plus 1.98 times 10 to the 20 Newton y hat. Or graphically, this will look like this will be the net force. So I think I can do the rest of the calculation in Wolfram alpha. So rest of the calculation is I need to figure out the magnitude of the net force, and that magnitude will be the square root of the x component of the net force squared plus the y component of the net force squared. Add them, take the square root, that will give me the magnitude. And then once I have that, then I'm going to work through the rest to divide up by the mass, which will give me the magnitude of the acceleration. So let me do all that in Wolfram alpha here. Yeah, around here. So square root of for the force, and here let me I will plug in all the number, all the units. That let me use Wolfram alpha to do this unit conversion and also double check my algebra. 4.36. I'm gonna use the E notation, E20. That means times 10 to the power of 20 Newton squared plus 1.98 E20 Newton squared. So that will give me net force. I guess I can do the whole thing in one shot. Divided by the mass. Yeah, I'm given the mass of the moon, 7.35 times 10 to the 22. So 7.35 E22 kilogram. And one of the nice thing about putting the units in is that suppose I made a mistake with where to put the square root. Like I put square root, like put mass inside the square root, which would be a mistake. If I do that, then the putting in the units will kind of show me something that will help me figure that out. So yeah, this should be in acceleration units. So let me get an answer. Let's see if it's in acceleration units. Kilograms for kg. Yeah, it understood me correctly. Newton per kilogram is there. Yeah, it's the same gravitational field strength, so I think it's got it, but since it's not giving me it in traditional acceleration units, I'll say in meters per second squared. And if somehow I made the algebra mistake and that's not one of the compatible units, then Wolfram alpha will complain. Otherwise, it'll give me this. And I could do the conversion from meters to millimeters myself, multiply by 1,000. So that would be 6.515. Or I can say let's get it in the unit that the question expects me to have in millimeters per second squared. So yeah, 6.515, and hopefully that's correct. And for significant figure, it's fine. I think I've mentioned how writing down all the significant figures makes it look unprofessional. But the way the Wolfram alpha presents it, they tend to kind of round it fairly reasonably, unless for whatever reason you want 6 or 7 significant figures, then you have to do something else. Yeah. So that's this question. Let me go to the other question and do it kind of as a group because the approach will be basically similar. Alright, so this is the other question. I thought they would be related, so that's why I'm doing that kind of together as group. Let's now read the question carefully. It says, two forces are applied to some mass. Let me just start labeling things so that I don't miss them. Some mass object, and it accelerates at we are given the acceleration, okay, in the positive y direction, okay. It's slightly more complicated than the other one. So so let me write down my acceleration is some acceleration y hat. It's in the positive y direction. If one of the forces acts purely in the positive x direction, yeah, that's what I thought was. So let me call this F1 as a vector. It's gonna be the F1 magnitude x hat. It says find the magnitude of the other force. Okay, let me just draw a sketch of this setup to make sure that I correctly understand it. I think the other force that I need to figure out, it'll have x and y component, and I'll need to take the magnitude of it. So let me first sketch the picture to make sure I didn't misunderstand anything. So I have some mass object, and I'm going to define my axis the normal, same, usual way, x and y, because the question is already referring to those axes, and it kind of makes sense to draw them straight. It's the same default, unless you have a good reason to do it differently. So they've given us a force F1 that's acting in the positive x direction. So this is my F1, and they've told us that this mass ends up with an acceleration in the purely vertical or y direction. This is the direction of acceleration, which means we kind of know the net force on the object. This is the direction of net force. So that's all the information that's given in the question so far. So let me write out this expression for net force just to make sure I don't make any algebra errors. Net force is given by the sum of the two forces, F1 that I labeled, and now I need to label F2. So here let me just solve for F2. So what F2 can be represented as in terms of the quantities we have been given, we are interested in, is move F1 over to the other side, so it's a net force minus F1. So F2 is a difference between these two forces. Or to put it precisely, it's the vector such that when you add it to F1, you get net force F. So F2 should be drawn, I think, like this. So I'm using adding to. So this is should be F2. So the way I'm double checking this, so I imagine adding these two vectors, head to tail. So F1 plus F2, which should cancel this out and give me net force. Also, that's the definition of net force. That gets me net force. So this is the graphical representation of F2. And I need to work it out. And in fact, I think I might have everything. Let's just to start writing down the algebraic expressions that we've been given. So we were given the net force in terms of acceleration. So let me just do one more step and just to write this down as ma minus f1. So m, and let's see, acceleration, I'll write it this way, 8 times y hat, ma y hat minus f1 is f1 x hat, so minus f1 x hat. Yeah, so the forces I add, they are, the vectors I add, they are only in the x and y directions. So let me just put this into standard form. So F2, its x and y component should be minus F1, that's its x component, x hat, plus its y component should be ma y hat. That's it. And for the purpose of the answer that they are looking for, I need the absolute value, the magnitude of this. I can do that in Wolfram Alpha. The formula I'll be using is the same one as the last time, the F2, the absolute value, the magnitude is the square root of F2, the x component squared, plus F2, the y component squared, square root. So let's do that. The x component is going to be minus F1, or 13.0 Newton, and I'll be squaring it and add it to the F2 y component, or mass times acceleration. That will be the mass, 4 kilogram, times the acceleration that we were given, 2.00 meter per second squared. And I square that for this portion of the expression here. I've added them, take the square root. So that should give me the magnitude. And I'm putting in all the units to make sure, that serves as a double check to make sure I didn't make any algebra error. It's the correct interpretation, 15.26, looks right. It's a little bit bigger than 13, yeah, that's probably right, 15.26, let's hope it's correct. I was 100% sure that it's correct. I wasn't necessarily 100% sure that there was no mistake in the program coding, because this is my first time. Yeah, so those are the two questions, and I try to do this in a kind of standard way, where basically anytime you're adding vectors, you can always add them in the component representation. That's a kind of the brute force standard way to do it. It'll always work. It's sometimes slightly less elegant than using like law of cosine or using these graphical things, but it'll always work. So that's really what I recommend that you do, unless you want to be a bit more fanciful and use law of cosine or do other geometry stuff.